First, I am going to say that the Wendy's is X bar 1, or X1 bar better. That equals 1.39066667 with a sample size N1 equals 30. I'm going to stop sharing and you can see this in a second. And the McDonald's X2 bar, which is 1.3893333, of course with N2 also 30. Then I'm going to record the median for sample 1, which is 1.2, the median for sample 2, which is 0.86. And as you see, we have multiple modes for Wendy's and no mode for McDonald's. Okay, so here's how I recorded the information. Wendy's, X1 bar, the mean for Wendy's, X1 bar, mean for McDonald's, X2 bar, sample size, and the median. Okay, now I would like us to look at the following two graphs. I don't have the histogram just yet. We did not discuss and we did not look at the histograms. But let's suppose the situation is, let's say, something like this. And let's suppose the situation is something like this. You can see, what are you graphing here? Well, I'm just imagining that I have all the histogram with the bars and everything. But the peaks of all bars create something like this. The peaks of all bars create something like this. Okay. Obviously, this is a bell shape. It's a bell-shaped distribution. Obviously, this one, what can we say about this one?
Right.
Very good, very good. You skew to the right. Yes, to the right. Very good. Skewed right. And I would like you to understand something before we look at the histogram, which is very important. For the bell-shaped distribution, the mean and the median, median, are very close to each other. They could be the same, but they're very close to each other. Here's what happens. One of these two measures of central tendency is not robust. And which one is, in other words, pooled? In this case, right. So the median of the distributions is always robust. The mean is not. Because see what happens? These numbers or these observations that are so much higher and pull the distribution to the right will also pull the mean with them. So in this case, the median will still be about the same. It has to be 50% above, 50% below. But the mean will always be pulled where the higher or lower observations are. More observations, like the skewed distribution is to the right, the mean is pulled. So the mean is not robust.
Does that apply to left skewed as well?
Of course. So let's very good question. Let's also show an example like that. Yes. So if I have something like this, the mean, I'm exaggerating, the mean will be here. The median will still stay in place. In other words, 50% and 50%. But the mean will be pulled by these observations that are much lower than the rest. In the case of a bell shape, pretty similar. They could even be the same. It may happen. So now let's look at our distributions again. So I'm going to share my screen. Good. I'm going to click on this. Good. So let's go to graphs. Let's go to histogram. Click on graphs and histograms. So let's take a look. Click on both Wendy's and McDonald's. We want percentages, relative frequency, in other words. Let's say we want to start at 0 because the times are between 0 and 5. And the width, I'm going to say 0.5. I meant 5. Now, let's choose markers. We want to see the mean. If you want to change the color, you can change the color. So mean is, in my graphs, will be green. And the median, which is robust, will be red. I want to label. Yes, why not? I want to label the x-axis, wait time. So I know what I'm doing. I want the y-axis to be labeled percentages. Okay, title, Wendy's, oops, versus McDonald's, wait time. And then let's compute. And let's see what happens. So see, the moment I changed the view, it distorted a little bit the histogram. So always be careful. So see what happens? I see a skewedness. Which one is pulled to the right more?
The mean?
Yes, as expected. The mean is not robust. The median stays in place. Okay, let's click on the arrow and see what happens here. Clearly, this is even more skewed to the right. And look what happened. The mean got pulled to the right even more. And here's the median that stays in place. Any questions on this concept, these concepts so far? Any questions?
Nope.
Okay. We are, now I need your input. Would you like to continue with the measure of dispersion? So right now in 3.1, we are looking at the center. Where is the center? What happens to the rest? What is the most important area? But we also want to know how spread the data is. And this is the measure of dispersion. So you want to go with the measure of dispersion, or you want to do some work in MyLab Math first on 3.1?
You do dispersion?
Okay. Very good. So let's continue with that. So moving on to 3.2. Measures of dispersion. Good. And here they are. So we're going to look at range. We use the range, which is the maximum value minus the minimum value, when we looked at the histograms. Why? Because we needed to determine the number of classes, and we needed to know where the maximum and the minimum was, and how we determined the class width. So we already know this. So since I have an example right here, the range will be, let's say if this is 150 and this is 20, for this example, the range will be 150 minus 20. If this is the maximum and this is the minimum, then the range will be, for this example, that will be 130. So there is nothing much to explain here. The next one is what is called standard deviation. So the standard deviation really tells us how far observations are from the mean. How far observations are from the mean. And yes, we have a formula. Of course, we have two formulas, one for, I think I'm on page 4. Yes, I'm on page 4. Of course, we have two formulas, standard deviation for the population and for the sample. Slightly different, careful with these two. The notation now. This is another sigma. And you can say, but you already showed us sigma. True. So that is also sigma. Okay. So the notation for this, or the formula for this, will be the square root, the sum of the differences from each observation minus the mean of the sample. Sorry. I'm talking about population. I cannot use sample. I have to use mu. Got carried away. So this is mu. I cannot use x bar, but I have to let it dry now. Divided by n, the sample size. And of course, squared. Now this one will be exactly the same. However, we're not going to divide by lowercase n. So the notation, however, this is the parameter and this is the statistic. Now we can use a little s. So this is the square root of the sum of xi minus x bar squared divided by n minus 1. So we're going to talk about this even a lot later. Degrees of freedom. In short, df is what we have here, n minus 1. So this is minus mu. Mu, the parameter, mu. So the question here is, I'm sure it's on your mind, why do I divide here by the entire population? And I divide here only by n minus 1. Why don't I divide by n? The reason is that the sum of xi for all of them, the sum of xi minus x bar will always equal 0. Not the squared one. Not the squared one. So I'm going to explain this further. Also, the sum from xi minus mu is always 0. But the squared will not be 0. So let me look at an example. So here it is. So let's say this is for a sample, size n, and I have x bar here. And I have all the observations. So let's say this is x1, this is x2, this is x3, this is x4. It is guaranteed that this distance is positive, this distance is positive, this distance is negative, this distance is negative, and it's guaranteed that the sum from xi minus x bar will always be 0. This plus this minus this, because they are negative, this will always equal 0. So coming back to my explanation, why I divide here by n is because I don't need to create any estimation or any inference. I got the parameter. If I get the parameter, if I get to everybody, there is no approximation, there is no error, assuming there is no entry error, data entry error. But here, I'm approximating this using a sample and determining the standard deviation for the sample. And yet, I do not divide by n, but I divide by n minus 1. Why? And this is called degrees of freedom. One more time, why? Because only n minus 1 have freedom of being anything. The nth one has to be fixed. What does it mean? So that this is 0. So as long as I get this to be 0, only n minus 1 observations can, or have freedom, can be anything. The nth one has to be fixed so that it ensures this. Here there is no need, because I got to everybody and I will never make an approximation or an estimation, or what we say with the correct word is inferential. I'm not making an inference about this from this. There is no need. I have them all. So keep this in mind. We divide by n minus 1. So now in the graphing calculator, where is my graphing? Oh, I don't need it. I have my, let me share, because this is very important to explain. So let's go to our calculator for a second. So let's go to lists. So let's go